Right now, inside a public archive on a server in Baltimore, a spacecraft that has been dead for years is still finding planets. Kepler ran out of fuel in 2018. NASA sent it one final goodnight command, shut down its transmitter, and let it drift into orbit around the sun. And yet, astronomers recently pulled a brand new world out of the very last week of data the telescope ever recorded. A planet that sat hidden in the noise for years while the machine that captured it tumbled silently through space. Nobody expected a retired spacecraft to keep making discoveries from beyond its own grave. Stick around, because I'm about to walk you through what scientists actually confirmed was hiding in Kepler's final data. And hit subscribe now, because this channel breaks down real space discoveries without the exaggeration. And stories like this one are exactly why the archives matter. Let's go back to where this story actually begins, because it starts a lot earlier than you might guess. 400 years before the spacecraft existed, there was a man hunched over a desk in Prague doing arithmetic by candlelight. His name was Johannes Kepler, and he had inherited something priceless from his late employer, the Danish astronomer Tycho Brahe. It was a mountain of observations of the planet Mars, decades of naked eye measurements, the most precise ever made at the time. Kepler spent years grinding through that data by hand, page after page of calculations, chasing a pattern in the way Mars wandered across the sky. He filled hundreds of pages with nothing but arithmetic. He called it his war on Mars. And buried in someone else's old data, he found the truth that had eluded astronomers for 2,000 years. Planets do not move in perfect circles. They move in ellipses, sweeping faster when they swing close to the sun and slower when they drift far away. It is worth pausing on that, because it set a template that this story is going to repeat in a way that feels almost poetic. The man the telescope was named after made his greatest discovery not at a telescope, but inside an archive of observations somebody else had already collected. Now jump forward to the 1980s, to a physicist named William Barucki, working at NASA's Ames Research Center in California. Barucki was not a famous scientist. He had spent his early career studying lightning and the physics of heat shields for the Apollo program. But he had become quietly obsessed with a simple idea. If a planet happened to pass in front of its star, the star's light should dim. Not by much, by a tiny, almost absurd amount. But if you could build a light meter sensitive enough, and if you could make it stare at thousands of stars for years without blinking, you could count planets around other suns without ever seeing a single one of them directly. The idea was elegant. The reception was brutal. Barucki proposed the mission to NASA in the early 1990s and was rejected. He tightened the design and proposed it again. Rejected. He built demonstrations to prove the detectors could reach the required precision, proposed again, and was rejected a third time, then a fourth. The review panels kept saying the same thing. The measurement was simply too delicate. Detecting an Earth-sized planet crossing a sun-like star means catching the star dimming by less than 1/100th of 1%. One reviewer famously compared it to spotting a flea crawling across a car headlight from miles away. For more than a decade, the answer stayed no. Barucki kept refining the proposal anyway, year after year, test after test. He and his colleagues built a small ground-based telescope called Vulcan to prove the detection technique on real stars, and ran laboratory demonstrations showing their detectors could hold the required precision even with the electronic noise, the pointing jitter, and the stellar flickering. The review panels kept worrying about. Each rejection came with a list of doubts, and Barucki treated the list like homework, methodically crossing off objections one by one until there was almost nothing left to object to. People who worked with him describe a man who simply never entertained the possibility of giving up, a quiet, stubborn engineer's confidence that the universe would cooperate if the instrument was good enough. And in December of 2001, NASA finally said yes. The mission was named for Johannes Kepler, which, given how this story ends, turned out to be more fitting than anyone could have known. It took another 8 years to design and build the spacecraft, and in March of 2009, a Delta rocket lifted off from Cape Canaveral carrying a telescope named Kepler, with a single instrument aboard, a photometer built around a camera with roughly 95 million pixels, at the time, the most powerful camera ever sent into space. Here is what made Kepler fundamentally different from every telescope that came before it. It did not slew around the sky chasing interesting targets. It did one thing with almost unsettling patience. It stared. NASA pointed it at a single patch of sky between the constellations Cygnus and Lyra, a region containing more than 150,000 carefully chosen stars, and Kepler watched that same patch continuously, measuring the brightness of every one of those stars every half hour for years on end. No sleeping, no weekends, no cloudy nights, just an unblinking electronic eye waiting for shadows. The method itself is beautifully simple once you see it. When a planet crosses the face of its star from our point of view, it blocks a sliver of the starlight, and the star appears to dim for a few hours. The depth of that dip tells you the planet's size, because a bigger planet blocks more light. The time between dips tells you the length of its year, and from the length of its year you can work out how far the planet sits from its star, which tells you how warm it is likely to be. 3 numbers pulled out of nothing but a flickering point of light. Astronomers had actually watched this happen in our own solar system for centuries, every time the Venus or Mercury crossed the face of the Sun. Kepler's job was to catch the same event around stars trillions of miles away, where the entire drama plays out inside a change in brightness smaller than a candle flickering in a stadium of floodlights. There was one more requirement, and it is the reason the mission's patience mattered so much. A single dip proves very little. A speck of dust, a flicker in the electronics, a spot rotating across the star's surface, any of these can fake one dip. What sells the discovery is repetition. The dip has to come back again and again on a perfect schedule, the same depth, the same duration, like a train that is never late. That is why Kepler had to stare at the same stars for years. It was not collecting pictures. It was collecting alibis, ruling out every alternative explanation until only a planet remained. And the shadows came. If you're enjoying this so far, take a second and hit the like button. It genuinely helps the channel, and I promise to keep explaining this the way I'd want it explained to me. No jargon, no hype, just the real story. The first major wave of discoveries rewrote the textbooks almost immediately. Within the first 2 years, Kepler confirmed a planet called Kepler 10b, a scorched rocky world not much bigger than Earth, circling its star so tightly that a year there lasts less than one of our days. Its daylight side is hot enough to keep an ocean of molten lava at a permanent boil. It was the first unambiguously rocky planet ever confirmed around another sun-like star, and it proved the telescope could do the very thing the skeptics had called impossible. Then came a world orbiting 2 suns at once, a planet where you could stand and watch a double sunset, something that until that moment had existed only in science fiction, and which the Discovery team happily compared to Tatooine from Star Wars. Then came planets in the habitable zone, that not too hot, not too cold band of orbits where liquid water can survive on a surface. One of them, announced a few years into the mission, was a world roughly 60% larger than Earth, circling a star remarkably like our Sun, on an orbit remarkably like our own, and headlines around the world called it Earth's older cousin. Then came entire solar systems packed tighter than the orbit of Mercury, 5 and 6 planets whirling around a single star like clockwork. And alongside the planets, the data kept coughing up things nobody was even looking for. Kepler caught the light of supernova explosions in their opening hours, something almost impossible to do from the ground because you cannot schedule a star's death. It recorded pairs of stars swinging so close to each other that they visibly stretched and rang like struck bells, a phenomenon astronomers took to calling heartbeat stars. And it found one star, flagged not by software but by citizen scientists browsing the raw data, whose light dipped in a way no planet could explain. Irregular, ragged plunges that at one point swallowed a fifth of the star's brightness. For a while, that one star was the most argued about object in astronomy, and the eventual explanation, most likely enormous clouds of fine dust, mattered less than what the argument proved. Ordinary people, looking at public Kepler data with patient human eyes, could find things that professional pipelines missed. Remember that detail, because it is about to become the heart of this story. One system, Kepler 90, eventually turned out to have 8 planets, tying our own solar system for the record, and the 8th was found years later by a machine learning algorithm trained to sift the old data, which tells you something about how deep this archive really goes. But the individual worlds, as strange as they were never really the point. The point was the census. Kepler was not built to find a planet. It was built to answer a question that humans had been asking for thousands of years without any way to test it. How common are planets? Before Kepler, the honest answer was that nobody knew. Planets around other stars might have been cosmic rarities, 1 in a million flukes. When astronomers ran the numbers on Kepler's Hall, the answer came back, and it was genuinely stunning. Planets are not rare. On average, there is at least 1 planet for every star in our galaxy. Hundreds of billions of worlds in our galaxy alone, and a meaningful fraction of them are small, rocky, and sitting in the habitable zones of their stars. It is worth sitting with that for a moment. Every star you can see on a clear night, statistically, is dragging at least 1 planet around with it. That fact, which schoolchildren now learn as if it were obvious, was measured by 1 spacecraft staring at 1 patch of sky. But the story was only half over, and the second half is where things start to go wrong. To hold its gaze perfectly still, Kepler relied on 4 spinning devices called reaction wheels. gyroscope-like flywheels that let the spacecraft steer itself without burning fuel. It needed 3 of them working to point precisely. 4 gave it exactly 1 spare. In July of 2012, one of the wheels began grinding and failed. The mission carried on, down to 3 wheels and 0 spares, and everyone involved understood the arithmetic. Then, in May of 2013, a second wheel seized. Just like that, the finest pointing machine ever flown could no longer hold still. The primary mission was over, and NASA came very close to shutting the whole thing down. What happened next is the kind of engineering improvisation that deserves to be far more famous than it is. Engineers at Ames and at Ball Aerospace worked out that sunlight itself could stand in for the broken hardware. Light exerts a real physical pressure, absurdly gentle but constant. If they oriented the spacecraft so that the pressure of sunlight pushed evenly across its solar panels like a canoe balanced against a steady current, that push could act as a kind of virtual third wheel. The trick only worked if Kepler kept its instruments aimed along the plane of the solar system, and it had to rotate to a new field every few months as the sun moved. But it worked. The telescope that could not hold still learned to lean on the sun itself for balance. NASA called the reborn mission K2, and instead of one patch of sky, it now swept its gaze along the zodiac in a series of observing campaigns, each lasting roughly 80 days. In its second life, the spacecraft studied clusters of newborn stars, watched asteroids and comets in our own solar system, and kept right on finding planets, hundreds of them, many around small red dwarf stars close enough for future telescopes to study in detail. At one point, it even trained its camera on a faint red star that another team had made famous, the one known to host 7 roughly Earth-sized planets, adding precious data about a system that has since become one of the most studied in the galaxy. The Wounded Telescope's second act produced science its designers had never even planned for, and it is worth being honest that the second act only happened because the first one broke. Had the wheels never failed, hundreds of known planets along the zodiac would simply not be in the catalog today. There was just one resource nobody could improvise around: fuel. Every rotation, every wobble correction, every downlink to Earth cost a little of the hydrazine in its tank, and here is the detail that tends to catch people off guard. Kepler had no reliable fuel gauge. Nobody builds one that works well in 0 gravity for a tank like that. Engineers could only estimate what remained from pressure readings and bookkeeping, which meant the mission was, in its final year, a running bet against an unknown number. By the summer of 2018, the signs of starvation were showing. Thruster performance was sagging. The spacecraft kept dropping into protective safe modes, the robotic equivalent of a dying patient slipping in and out of consciousness. And this is the part of the story I find genuinely moving. The flight team knew the end was weeks away at best, and they chose to spend those weeks observing. In September of 2018, Kepler opened its eye one last time for its 19th extended mission campaign, aimed at a fresh field of stars, and started recording. It managed only about a month of observation before the fuel finally gave out, and only the first week or so of that data was clean and steady, because as the tank emptied, the pointing began to wander, and the images smeared. Getting that data home was its own small drama. A downlink is not a casual thing. The spacecraft has to rotate away from its targets, aim its antenna at Earth, and hold that aim steadily enough for NASA's Deep Space Network, the trio of giant radio dishes in California, Spain, and Australia, to lock onto a whisper of signal from tens of millions of miles away. With thrusters misfiring and the tank essentially dry, nobody was certain Kepler could hold the pointing long enough to empty its recorder. The flight team scheduled the antenna time, sent the commands, and waited. The spacecraft turned, steadied itself one more time, and delivered. Every last usable byte of that final campaign came down safely before the hardware gave out completely. On October 30th, 2018, NASA announced the mission was over. 2 weeks later, controllers transmitted the goodnight commands that switched off the transmitter for good. And by a coincidence that nobody planned and everybody noticed, that final farewell was sent on November 15th, the anniversary of the death of Johannes Kepler himself. The spacecraft went silent. The data did not. By the way, I'd genuinely love to know in the comments which of these missions you'd want covered next, the ones that ended decades ago or the ones flying right now, because reading those comments is honestly how I decide what stories to tell on this channel. So now we arrive at the discovery this whole story has been building toward, the one that tends to stop people in their tracks once they understand what it actually means. And to appreciate it, you have to picture the state of the final data set. Imagine a photographer, hands trembling, taking one last roll of pictures while walking. And then imagine being asked years later to find something in those blurry frames that nobody has ever seen before. That is roughly the challenge this data presented. That final week of clean data, recorded by a dying spacecraft with failing thrusters, sat in the public archive for years. Professional planet hunting software struggles with a data set like that. It is short, It is noisy and it ends abruptly, which is close to a worst-case scenario for automated searches that thrive on long, steady stretches of observation. A transit signal needs to repeat for software to trust it, and in 1 week of wobbly data, a planet might only cross its star once or twice. But software is not the only thing reading Kepler's archive. There is a community of veteran citizen scientists, ordinary people, some retired, some doing this after work, who have trained their eyes over years to recognize the dip of a planet crossing a star in a raw light curve. They scroll through brightness measurements by hand, star after star, the way Johannes Kepler once worked through Tycho Brahe's ledgers. And when a small team of astronomers working alongside these volunteers combed through that final campaign, they found them. Planet-shaped shadows, hiding in the very last week of Kepler's life. Finding the dips was only step one, and this is where the years of delay came from. With so little data, the researchers had to rebuild the case for each signal almost from scratch. They checked whether the dips could be caused by the wobbling of the dying spacecraft itself, since failing thrusters smear starlight in ways that can mimic a transit. They checked whether a faint background star, an eclipsing pair of stars blended into the same pixel, could be faking the signal. They went after the targets with ground-based telescopes, measuring the host stars carefully, and in at least one case they caught an additional transit from the ground, years after Kepler's death, arriving right on the schedule the old data predicted. A dying robot made a forecast, and living astronomers watched it come true. Careful follow-up work confirmed 2 new planets from that dying breath of data, with a third candidate that researchers have not yet been able to fully confirm. The confirmed worlds orbit small red dwarf stars, and both appear to be a bit smaller than Neptune, gassy worlds on quick orbits of roughly a week or 2. Neither is habitable. That was never the point. The point is when the measurements were made. Astronomers involved in the work have described these as quite possibly the final planets Kepler will ever be credited with from that last campaign. The closing entries in a ledger that started with a stubborn engineer and his rejected proposals. Every catalog has a first line and a last line, and we may just have read Kepler's. These are, in a very real sense, the last worlds Kepler ever saw, discovered years after the telescope that recorded them stopped existing as a functioning machine. A spacecraft with empty tanks and smeared vision, weeks from death, was still doing its job so well that its final glances contained undiscovered planets. Now, to keep this honest, I want to be clear about what Kepler could and could not do, because the limits matter as much as the triumphs. Kepler never photographed a single one of its planets. Every discovery was a shadow, an inference from starlight, which is why confirmation by other telescopes matters so much. The transit method also has built-in blind spots. It only catches solar systems' tilted edge onto our line of sight, and it finds close-in, fast-orbiting planets far more easily than twins of Earth on slow, patient orbits. For every confirmed planet in the catalog, there are thousands of candidates still waiting in a kind of scientific purgatory, flagged but unverified, because follow-up telescope time is scarce and expensive. The census is real, but it is a census taken through a keyhole, and researchers are refreshingly upfront about that. It is also worth remembering what this all cost, because the answer surprises people in both directions. Kepler's development and launch came in at roughly $600 million, with the extended years adding more on top. That is real money. It is also, for scale, in the neighborhood of what a single big-budget film franchise spends. And for that price, humanity got the first honest census of planets in its galaxy, a working answer to a question philosophers had argued about since ancient Greece. Every extension of the mission had to survive a competitive review, teams of scientists arguing on paper that another year of this aging, wounded spacecraft was worth more than the alternatives. It kept winning those arguments for a simple reason. The data kept being worth it. Even so, the numbers are the numbers. More than 2,600 confirmed planets from the primary mission alone, thousands more candidates, and a legacy total that still accounts for an enormous share of every planet humanity has ever found. Now, picture for just a moment what it would actually be like to stand on one of those last 2 worlds. You're on a planet a few times wider than Earth, deep in the glow of a red dwarf sun. That star hangs in your sky far larger than our sun ever appears from Earth, but cooler, redder, more like an eternal sunset than a daylight sky. Your year, the entire trip around that sun, is over in about the time an Earth week takes, and somewhere across hundreds of light years of darkness in a direction you could not pick out from any other patch of that alien sky. There's a small blue world where a machine noticed you exist in the last week of its working life, and where people found the note it left behind years later. Light is still leaving your red sun right now, carrying the same tiny shadows toward Earth, and nothing about the story requires anyone to be watching anymore for it to be true. The universe keeps broadcasting. We just have to keep checking the recordings. So, what does all of this actually add up to? I think it adds up to a quiet redefinition of what a telescope even is. We tend to picture discovery happening at the eyepiece. In the moment, live. Kepler's afterlife proves that the real instrument is the archive. The entire dataset lives at a public archive hosted in Baltimore alongside data from Hubble and Webb. And anyone reading this can download it tonight, for free, no credentials required. Students have found planets in it for class projects. Retirees have found planets in it from their kitchen tables. There are stars in that archive whose light curves no human being has ever actually looked at with their own eyes, which means, in a very concrete sense, there are almost certainly still planets in there, waiting right now. The spacecraft was just the collection phase. Every light curve it ever recorded is public, sitting on those servers in Baltimore, free for any scientist, any student, any obsessive night owl with a laptop to search. Machine learning tools keep getting better, and every few years, someone teaches a new algorithm to reread the old data, and it surfaces worlds everyone else missed. The telescope died in 2018. The mission, in any sense that matters, did not. There is also a torch being carried forward. Kepler's direct successor, a survey telescope called TESS, has been sweeping nearly the entire sky since 2018, applying the same transit trick to the brightest, closest stars, and it has already racked up thousands of planet candidates of its own. Every technique Kepler pioneered, the unblinking stare, the statistical confirmation, the public archive, the partnership with citizen scientists, is now simply how planet hunting works. That is the deepest kind of legacy an instrument can have, the kind where its methods outlive its hardware so completely that people stop noticing where they came from. And the census Kepler started is about to be blown wide open. NASA's next great survey observatory, the Nancy Grace Roman Space Telescope, is designed to hunt planets in a way Kepler never could, catching worlds by the way their gravity briefly bends the light of background stars, a technique that can find planets in wide orbits and even lonely rogue planets sailing between the stars. Astronomers expected to add tens of thousands of new worlds to the count, and its first images are a story all their own, one I'm covering on this channel, so subscribe and ring the bell if you have not already, because the age of finding planets is not ending, it is accelerating. Thanks for watching, and I will see you in the next one.